This video will cover the use of reductive amination to synthesize amines. Typically, when we say synthesis of amines, what we really mean is the addition of R groups to an amine. For example, if we add an R group to ammonia, we make a primary amine. We can make a secondary amine by adding an R group to a primary amine. And finally, we can make a tertiary amine by adding an R group to a secondary amine. Typically, it's this kind of process that is meant when people talk about the synthesis of amines. One way to carry out this type of synthesis of amines, adding R groups, is through reductive amination. Reductive amination adds an R group to an amine through an imine intermediate. Combination of an amine with a ketone or aldehyde in the presence of an acidic catalyst forms the imine, which can be reduced to form a new amine with an additional R group. The specific method of reduction depends on the exact structure of the imine, whether it's primary, secondary, or tertiary. Next, let's look at some examples. We will start with the synthesis of primary amines from ammonia. Remember that this process takes ammonia and converts it to a primary amine. Typically in these reactions, hydroxylamine is used in place of ammonia. In this reaction, hydroxylamine is treated with a ketone or an aldehyde in the presence of an acid catalyst. This produces the oxime intermediate. Finally, the oxime is reduced to produce the primary amine. The reductive step can be carried out in several ways. The oxime can be reduced to the primary amine using hydrogen and a transition metal catalyst like palladium, platinum, or nickel. Alternately, it can be reduced using sodium borohydride. Finally, lithium aluminum hydride can also be used to reduce the oxime to the primary amine. The reductive step can be carried out in several ways. The oxime can be reduced to the primary amine using hydrogen gas and a transition metal catalyst, such as palladium, platinum, or nickel. Alternately, it can be reduced using sodium borohydride. Finally, lithium aluminum hydride can also be used to reduce the oxime to the primary amine. Next, we'll consider the synthesis of secondary amines. This process converts the primary amine into a secondary amine by adding an R group. In this synthesis, the primary amine is treated with a ketone or aldehyde under acidic conditions to produce the imine. The imine is reduced to produce the secondary amine. The reduction of an imine to a secondary amine can be carried out in two different ways. Either sodium borohydride can be used, or lithium aluminum hydride. Finally, let's look at the synthesis of tertiary amines. This process converts the secondary amine to a tertiary amine, again by adding an R group. This synthesis starts by treating a secondary amine with a ketone or aldehyde in the presence of an acid catalyst. This forms the iminium ion. Because a secondary amine only has one proton to leave, the nitrogen in the imine that is formed must have a positive charge. Therefore, this is an iminium ion. The iminium ion is unstable because of this positive charge, and so this equilibrium favors the carbonyl in the amine. Therefore, the majority of the species in solution are the secondary amine and the ketone or aldehyde. The final reduction step produces the tertiary amine. When determining what reducing agent can accomplish the transformation from the iminium ion to the tertiary amine, we have to consider the fact that the first equilibrium favors the carbonyl. Because of this, we need a selective reducing agent so that we can reduce the iminium ion and not the starting carbonyl. A more selective reducing agent, in other words, a less reactive reducing reagent that is commonly used for this type of reductive amination is called sodium cyanoborohydride. Sodium cyanoborohydride is similar in structure to sodium borohydride, except that one of the hydrogens is replaced by a cyanide ion. The cyanide ion is electron withdrawing and therefore reduces the nucleophilicity of the hydride ions that are attached to boron. This makes this reagent less reactive than sodium borohydride and therefore more selective, capable of reducing the iminium ion and not the starting carbonyl. Another reducing reagent that is sometimes used for the reductive step is sodium triacetoxy borohydride. Remember that this is the same less reactive reducing reagent that we used previously to reduce an aldehyde in the presence of a ketone. This selective reducing reagent is also capable of reducing the iminium ion in the presence of the starting carbonyl compound.